Hi, I'm Herb Gross, and welcome to lecture number 30 in our series Gateways to Algebra, where today we're going to be talking about division of polynomials, a topic that traditionally gives people a lot of trouble, and yet it's one that I find very, very fascinating. It's one of my favorite topics, primarily because I think it's so simple once you see the connection between this and regular whole number division. See, what I want to do today is sort of to complete our analogy that basically the arithmetic of polynomials is word for word the same as the arithmetic of whole numbers in place value, with the only difference that instead of talking about instead of 10 being the place value denomination, see, 10s, 10 squared, 10 to the thirds, we use what? X squared, x to the third, etc. So, for example, let's just take a look at something over here. Where does division come from? Division is the inverse of multiplication. In other words, once you know how to multiply, if we leave out one of the factors and give you one factor in the product, that becomes a division problem. Let's review this by going over multiplication of polynomials again. Suppose I want to take x plus 1 and multiply that by x squared minus x plus 1. Let's suppose I want to do that. Okay? What was the rule for multiplying? First of all, whenever we see subtraction, we can always replace it by add the opposite. So instead of writing x squared minus x plus 1, let's write x squared plus the opposite of x plus 1. By the way, from now on, I'm going to try to call this the opposite of x rather than negative x, because nothing prevents us from choosing x to be negative itself. This is just an aside. I don't want to confuse you. See, suppose x happens to be negative 7. What's the opposite of x in that case? See, not negative x, what's the opposite of x? If x is negative 7, the opposite would be positive 7. And psychologically, people say, how can a negative be positive? See, what we're saying is that when the so-called negative sign modifies a variable, we think of it as not being negative, but rather being the opposite. At any rate, let's go ahead now. The x has to multiply each of these terms. That means that the exponent involving x is going to increase by 1. So when x multiplies x squared, it becomes x to the third. When x multiplies the opposite of x, it becomes the opposite of x squared. And by the way, I may still say negative x just out of habit, but don't worry about that. And when 1 multiplies x, that becomes x. Now the 1 also has to multiply each of these 3 terms. That means those 3 terms just get written down again. Now let's see what happens over here. There's an x to the third. Here's an opposite of x squared along with an x squared. They're going to cancel when we add. Here's an x and the opposite of x. They're going to cancel. And I'm left with x to the third, x cubed, plus 1. In other words, by using multiplication, I've now shown that the polynomial x plus 1 multiplying the polynomial x squared minus x plus 1 gives us the polynomial x cubed plus 1. Here's where division comes in. Suppose now I decide to leave out the second factor. And I say to you, what must we multiply x plus 1 by to get x to the third plus 1 as the product? In other words, what must I put in the parentheses here to make this a true statement? And by the way, you can guess whatever you want. You can guess whatever you want. What happens is, after you make your guess, you just check to see if it's going to work. For example, let me show you a naive way of tackling this problem. Person says, let's see, to get from x to the third, I'll just multiply by x squared. And to get from 1 to 1, I'll just multiply by 1. Therefore, I expect x squared plus 1 to work. Well, certainly, x times x squared is x to the third. And 1 times 1 is 1. Why doesn't this work? Because to multiply, you don't just multiply the 2 first terms and the 2 last terms. It's what? Every term in the first set of parentheses has to multiply every term in the second set of parentheses. So you get the x to the third plus 1, see, but you also get 2 extra terms. Let's take a look and see why. X times x squared is x to the third. X times 1 is x. 1 times x squared is x squared, and 1 times 1 is 1. Here's your x to the third plus 1, but you also got what? An x and an x squared term in here. So in other words, we know that when we divide it, and by the way, the correct answer to this problem would be called what? X to the third plus 1 divided by x plus 1. And what we've just shown, by the way, even negative results can be positive. The one thing we have shown is what? That when you divide x to the third plus 1 by x plus 1, the answer isn't x squared plus 1. Unfortunately, we'd like to know what the answer really is. So to get an idea of what's going on here, let's see how we do this in the case of long division using whole numbers. Suppose I wanted to find out what number I had to multiply 13 by to get 2,821. Well, look, I know that 13 times 2 is 26. Therefore, what's 13 times 200? 13 times 200 would be what? 2,600. Therefore, whatever number I put in here, it has to be bigger than 200, because 13 times 200 would only be 2,600. Well, what if I had 300s? 13 times 3 is 39, so 13 times 300 would be 3,900. That's too big. So I know that whatever number goes in here, what must it be? It must be more than 200, but less than 300. Rather than guess this way, I can now make some adjustments. I say, look, there's at least 213s in here. 213s is worth 2,600. So what would that leave me with? I would still have 221 left to account for. By the way, if I'm bad at multiplication, I can put to the side over here the 13 table and refer to it whenever I want. For example, how many bundles of 13 can I take out of 221? Since 13 times 1 is 13, 13 times a 10 would be 13 tens, or 130. 13 times 2 tens would be 260. 260 is more than what I have, so what could I do over here? If I subtracted 130, wouldn't that take care of 10 more 13s? And what this would say is, after I've multiplied 13 by 210, I still have 91 left in order to get to the 2,821. How many times does 13 go into 91? It goes in 7 times. And so how many 13s were there altogether that I had to add up to get 2,821? There were 200 plus 10 plus 7. By the way, if you want to check this, just multiply. See, what is the 217th number you come to when you're counting by 13s? Just multiply 13 by 217. And I'm deliberately putting the bigger number on the bottom here because I want to show you something that's interesting. And for those of you who feel uncomfortable putting the big number on the bottom because you were taught to do that the opposite way in school, the only reason for putting the bigger number on top is so that there'll be fewer rows when you write this, and that will save paper for you. You see, there's going to be 1 row for each digit in the bottom number. If I put the 13 on the bottom, there'll only be 2 rows. But with the 217, there'll be 3 rows. But it doesn't matter. 7 times 3 is 21. Put down the 1, carry the 2. 7 times 1 is 7, and 2 is 9. 1 times 3 is 3. 1 times 1 is 1. 2 times 3 is 6. 2 times 1 is 2. Add these up. There's my 2,821. All I wanted you to see is, especially if I put in these zeros, do you see what 3 numbers I'm adding up here? 91, 130, 2,600. What numbers was I subtracting here? 91, 130, 2,600. Does this show you kind of vividly how division is the inverse of multiplication? By the way, this isn't the way most of us learned to do the division. If I recall, if you learned the same way I did, we did something like this. We said 13 goes into 28 twice. We put the 2 up here, put down the 13 times 2 was 26. We subtracted. 13 goes into 22 once, gave us 13. Subtracted gave us 91. Remember doing it this way? And the point I wanted to bring out was when we put the 26 over here, see this 2 over here was put above the 8, wasn't it? So even though the adjective was 2, the placement made it 200, you see? And 213s isn't 26, it's 2,600. This isn't really 13 because this was over the 2, which is in the 10th place. That was 130. If I put these zeros in, see if I bring this stuff down, put these zeros in, look at this and look at this. And notice that they're exactly the same. Now the reason I want you to notice this is I'm going to show you in just a minute or two that this is exactly the same thing we're going to do when we divide polynomials. We're going to come back to that same problem we were doing before, but let me just show you one more trick first. To me, division was one of the hardest operations I learned as a youngster in elementary school because they kept telling us what to do and it never worked. See, I was told, take the first digit here and divide it into the first digit here, and that tells you what number to put up here. Well, see, what happened to me was, when I did that, maybe this happened to you too. I said 1 goes into 1 once, and I put the 1 over here. Then I put the 11 down here, and I said, oops, I'm stuck. He said, well, that's right, because that was too big. What you have to do now is don't look at the 10, look at the 100. How many times does 1 go into 10? I said 10 times. No, you can't use the 10 because it can only be one digit per place value column. You have to try a 9. Okay, so I tried the 9. So I put the 9 over here, and to remind me that I was looking at the 100, the 9 went right over the 100. Then we said what? 11 times 9 is 99. Then we subtracted, we got 1. We brought down the 1. Then we said 11 goes into 11 once, and the answer was 91. Now, I want to show you what would have happened if at this stage in my career I happened to have known negative numbers. Let me just show you something kind of interesting. What would I have done over here? I have to subtract 11 from 10, don't I? But how do you subtract? You add the opposite. So I'll change these signs. So instead of 1, 1, it's negative 1, negative 1. 1 and negative 1 adds up to 0. 0 and negative 1 adds up to negative 1. See, I'm not worried if something is if I'm taking away more than what I have, because I have negative numbers now. How many times does 1 go into negative 1? What do you have to multiply 1 by to get negative 1? The answer is negative 1. So we put a negative 1 up here. The 1 times the negative 1 gives me negative 1. The 1 times the negative 1 gives me negative 1 again. How do I subtract? I add the opposites. Negative 1 and 1 drop out. 0 and positive 1 is 1. Now I bring down the 1. 1 goes into 1 one time. 11 times 1 is 11. This comes out to be 0. What's my answer? 1, negative 1, 1. But how do we read this? The 1 is in the hundredths place, so it's 100. The negative 1 is in the tens place. That means you're subtracting 10. And this 1 is in the ones place. That means you're adding 1. So how do you read this answer? It's 100 minus 10 plus 1. Well, 100 minus 10 is 90, plus 1 is 91. That's exactly the same answer I got this way. Now, I'm not telling you to do the problem this way. Obviously, this was a lot easier than doing this. But what did this do for me? It allowed me not to have to borrow. It allowed me not to have to worry about whether the product I got was too big, because I could always write it negatively. But here's the real amazing part. Let me write this over again, what we got. Remember, this is what it looked like, right? Now, suppose instead of these being ones, tens, hundreds, and thousands, I said, oh, I forgot to tell you. These are ones, x's, x squareds, and x to the third. I'm doing polynomial place value here, not whole number place value here. Well, what would 1, 1 denote? Wouldn't that be x plus 1? What would 1, 0, 0, 1 denote? Wouldn't that be x cubed plus 0x squared plus 0x plus 1? And how do you know that? Do the same thing you did in place value. Go back furthest to the right. The first digit is the ones place. This is ones, x's, x squareds, x to the third. And so what's happening is when I'm doing this problem over here, what I've really shown is what? That if I want to find out what I have to multiply x plus 1 by to get x cubed plus 1, all I'm going to do is what? I'm going to take x cubed plus 1 and divide that by x plus 1. And how does that division work? It works exactly the same way as place value division works. See, if I do it this way, I have to be careful. See, I still say what? X goes into x to the third, x squared times. So I'd have to put an x squared up here. Then I'd say x times x squared is x to the third. 1 times x squared is x squared. Now to subtract, I add the opposite. That gives me negative x squared. X goes into negative x squared, negative x times. You see, what's happening is, by using the place value notation, I don't have to worry about these nouns. But they're equivalent. I mean, practice going from this way to this way. I just, in the interest of time, I'm not going to bother doing that right now. But see, here's what we now have shown. See, in other words, what I've now shown you is what? That x cubed plus 1 is x plus 1 times x squared minus x plus 1. And that's a very interesting pattern. You see, this didn't have to be an x and a 1. It could have been an a and a b. And this would have been what? A squared minus a times b plus b squared. In other words, we now have another factoring recipe that may turn out to be interesting for you. It simply says what? If you take a plus b and multiply that by a squared minus ab plus b squared, you'll wind up with what? Just multiply this whole thing out. This would be a to the third minus a squared b plus ab squared. See, I'm multiplying each of these terms by a. Now I'm going to multiply each of these terms by b. That's going to give me a squared b minus ab squared plus b to the third. Now the minus a squared b and the plus a squared b will cancel. The ab squared and the negative ab squared will cancel. And all I'm left with is a to the third plus b to the third. And in a similar way, if I make this minus and this plus, a minus b times a squared plus ab plus b squared would give me a to the third minus b to the third. In other words, in terms of new recipes, the sum and difference of two cubes factors as follows. If you want to factor the sum of two cubes, just write the a plus the b. Then in the parentheses, you put in what? An a squared, an ab, and a b squared, and the middle term is negative. See, with the plus sign, the middle term is negative. With the minus sign, the middle term here is positive. So for example, to apply this principle, if a were 2 and b were 3, this would be x to the third minus 8. That can be written as what? X to the third minus 2 to the third. That would give me what? X minus 2 times what? X squared plus 2x, see, 2x plus 4. Notice you don't multiply by 2 like we did in squaring. This is just a different formula here. By the way, as a check, we can multiply this whole thing out. If x multiplies x squared plus 2x plus 4, we get x to the third plus 2x squared plus 4x. If negative 2 multiplies x squared plus 2x plus 4, we get negative 2x squared minus 4x minus 8. Everything cancels out over here, except what? The x to the third and the minus 8. So in other words, in the language of division, this says x to the third minus 8 divided by x minus 2 is x squared plus 2x plus 4. But suppose you didn't know how to factor this. Could you still take x minus 2 and divide it into x cubed minus 8? Sure you could. Now let's write it in place value language. The x place is a 1. The 1's place has a negative 2 in it. Now what do we have over here? We have 1x cubed. Now we need place value here. No x squareds, no x's, and negative 8 in the 1's place. So 1 goes into 1 one time. Where do we put the 1? Two digits here, 2 digits here. We put the 1 over here. 1 times 1 is 1. Negative 2 times 1 is negative 2. How do we subtract? We add the opposite. This drops out. This becomes a 2. Bring down the next digit. It's a 0. 1 goes into 2 twice. Bring the 2 up here. 2 times 1 is 2. 2 times negative 2 is negative 4. How do we subtract? We add the opposite. The 2 and the negative 2 drop out. 0 plus 4 is 4. Bring down the negative 8. 1 goes into 4 4 times. 4 times 1 is 4. 4 times negative 2 is negative 8. How do we subtract? We add the opposite. Everything drops out here. What's the answer? 1, 2, 4. But what's the code? 1's, x's, x squareds. The answer is what? 1x squared plus 2x plus 4. And by the way, this just works over and over again. You see, in order to make this look more effective for you and not have to check anything, I'm going to each time start with the multiplication problem and then show you how the division problem goes. Suppose I said to you, multiply x squared plus 3, okay, by x to the fourth plus 2x plus 1. So the x squared has to multiply each of these terms. That means the exponent is going to increase by 2 for each of these 3 terms. So the x to the fourth becomes x to the sixth, the 2x becomes 2x to the third, and the 1 becomes x squared. Now the 3 multiplies each of these. So the x to the fourth becomes 3x to the fourth, the 2x becomes 6x, and the 1 becomes 3. Now we combine like terms. There's a x to the sixth over here, there's an x to the fourth term, okay? There's an x to the third term, there's an x squared term, there's an x term. Nothing combined, so we just rearrange the order here. So the answer to this problem is x to the sixth plus 3x to the fourth plus 2x to the third plus x squared plus 5x plus 3. Okay, that's a multiplication problem. Now, what division problem do we give the person? Leave this out. We say, what do you have to multiply x squared plus 3 by to get x to the sixth plus 3x to the fourth plus 2x to the third plus x squared plus 6x plus 3. In other words, written as a division problem, it's this divided by this, and written as, I guess, a gazinta problem, you know, something gazinta something else. it's this number here goes into this one. And by the way, in terms of our code, what do we have here? A 1 in the x squared place, nothing in the x place, and 3 in the 1's place. Here we have what? A 1 in the x to the 6th place, a 0 in the x to the 5th place, a 3 in the x to the 4th place, a 2 in the x cubed place, a 1 in the x squared place, a 6 in the x place, and a 3 in the 1's place. Which basically just says this, doesn't it? See, I'm just writing it this way. How does this problem work? 3 digits here, 3 digits here. What do? 1 goes into 1 one time. 103 times 1 is 103. How do you subtract 103? You add the opposite. And what happens is when I do this, everything drops out. That's nice. Now what do? I bring down the 2. Okay? Remember, I have to have what? 3 digits. 3 digits for something. In other words, there's a 1, a 0, and a 3. So certainly 103 won't go into 2. 103 won't go into 21. 103 will go into 216. And by the way, every time I bring something down, just like in regular division, I have to put a 0 in as a placeholder to remind me that nothing went into this. In other words, I brought down the 2, 103 didn't go into 2. I brought down to 1, 103 didn't go into the 21. I brought down the 6. Now the 1 goes into the 2 times. Since I have 3 digits here, what can I do? The 2 times 1 is 2. 2 times 0 is 0. 2 times 3 is 6. Now what do? I subtract. How do you subtract? Add the opposite. And if I do that, this drops out. 1 minus 0 is still 1. 6 plus negative 6 is 0. Now I bring down the 3. 1 goes into 1 once. 103 times 1 is 103. To subtract, I add the opposite. This drops out. And what's the answer going to be? 1, 0, 0, 2, 1. Okay, now what does it stand for? The 1 is in the 1's place, right? The 2 is in the x place. This is x third, x squared, x third, x fourth, isn't it? See, 1's, x's, x squared, x third, x fourth. So what's the answer here? There's 1 in the x fourth place, no x cubes, no x squareds, 2 x's, and a 1. Okay? And what was the answer that we got before? Did I write this down? This doesn't matter. I just was wondering if I had it down here. Yes, it was x to the 4th plus 2x plus 1. Do you see how this thing works? Now, by the way, there can be remainders. Sometimes things may look like they should work nicely. Remember we said if there was x plus 1 over here, and inside was x to the 3rd plus 1, everything came out nicely with no remainder. Let me just change this to a minus sign now and see what happens. In other words, there's a 1 on the x place, and on the 1's place is a negative 1. There's what? A 1 on the x to the 3rd place here. There are no x squareds, no x's, and a 1. So how does the division work here? 1 goes into 1 one time. We put the 1 up here. This becomes what? 1 and negative 1. To subtract, we add the opposite. This drops out. This becomes a 1. Bring down the next digit, which is a 0. 1 goes into 1 once. 1 times 1 is 1. 1 times negative 1 is negative 1. To subtract, we add the opposite. This drops out. This becomes 1, 1. Now, 1 goes into 1 once. 1 times 1 is 1. 1 times negative 1 is negative 1. To subtract, we add the opposite. And be careful, don't be careless. This now becomes 2. In other words, the remainder is 2. What does that tell me the answer is? The answer tells me that the answer is what? There's 1 in the 1's place, 1 in the x place, and 1 in the x squared place. In other words, the answer to this problem is what? It's x squared plus x plus 1 plus the remainder of 2. In other words, if I were to multiply x minus 1 times x squared plus x plus 1, and then add on the remainder of 2, then I should get what? X cubed plus 1. And I think that might be a nice thing to close on to see if it works. In other words, is it true that if I take x minus 1 and multiply it by x squared plus x plus 1, and add 2 onto that, the answer will be x to the 3rd plus 1. And by the way, before I answer that, notice why this is not a factored form. You see, if there's no remainder, it's factored. If there's a remainder, that gives us an extra term over here. But let's just do this. What's the x going to do? It's going to multiply each of these terms. So this becomes what? X to the 3rd plus x squared plus x. Now the negative 1 multiplies each of these terms, giving me what? And I'm going to line these up in the interest of space. The x squared becomes negative x squared. The x becomes negative x, and the 1 becomes negative 1. So this drops out. What's left over here? X to the 3rd minus 1. See, that shows me that I didn't get the right answer yet. See, I want the answer to be what? X to the third plus 1, but what haven't I done yet? I haven't added on my 2. See, x to the third minus 1 plus 2 is x to the third plus 1. Okay? Now, again, there's only so exciting you can make this stuff because we do have to go through certain fundamentals. In other words, as exciting as baseball may be, it still may be tedious to learn all the rules. As exciting as it may be to play chess, it may still be tedious to learn all the rules. But if you don't just memorize the rules, but get a feeling from them, for them, you're not going to do very much with them. So I want you to get used to the arithmetic of polynomials, and later we'll get into using them. But for now, as a quick summary of what we did today and in the last few lessons, do you begin to see what I mean by saying if we really understand whole number arithmetic, polynomial arithmetic almost comes to us free of charge? That it is really a very basic type of thing, but it's a very important thing. So at any rate, we're going to start solving some polynomial equations next time when we talk about quadratic equations. But until next time, study hard, have fun, stay young. See you soon.